Hey, welcome back for another round of astronomy. Let's keep going. So, where we left off last time, we were doing the main sequence fitting and estimating distances to galaxies, or excuse me, not galaxies, stars, based off of the main sequence fitting. This next type of method is going to be giving us gives us the ability to measure to galaxies. Okay? And as it suggests, right now we're limited to the Milky Way with the main sequence fitting. But the next method, using Cepheids or variable stars, will now allow us to get to nearby galaxies. Say nearby. Okay? So let's go ahead and get an idea about that. So a more general term used is variable stars. And I first want to give you an idea about the process by which a star becomes a variable star. It's a particular location on the HR diagram. So here I've given you an HR diagram. What I have right here is the main sequence going from the lower right to upper left. And the issue is that there are particular spots on the HR diagram that when a star passes through those regions, it becomes a variable star. The main location is right here. This dashed line with this yellow hatched mark is the classic Cepheid variable stars. And these are the ones that we're going to really be dealing with. You can imagine, however, that as a star, say an O-type star, moves off of the main sequence, at some point it's going to pass through this Cepheid variable region, and therefore it'll be a variable star for a brief part of its lifetime. And of course, you can also see that, okay, well, if it goes to a helium flash and then comes back down on the horizontal branch, a given star might actually pass through this Cepheid variable region several times during its life. Okay? So let me give you an idea about why this variability occurs in the first place. And where we have to start is with the outer layer of the star. Okay? Imagine for a moment that you have a material that when it is a low temperature, it becomes opaque. In other words, at low temperatures, the layer does not let light come through. It blocks the light from escaping the star. That's where our starting point is going to be. What are the consequences of that occurring? So if you have this opaque outer layer and light is not permitted to escape out into space, what happens to the temperature of the outer layer? Well, if the light is not allowed to escape, that traps the energy in the star, if you will, and so the temperature of the star, the outer layer, will increase. So that heats the outer layer of the star. Well, what happens if the outer layer of the star is at a higher temperature? The molecules that make up the outer layer of the star, if it's heating up, those molecules are moving faster. And if they can move faster, that means that the entire outer layer will expand. So you start off with an opaque outer layer that traps the light in the star. The outer layer warms up, and so the entire star will expand. Now here's the kicker, is that if it's cool enough, the layer, instead of being opaque, becomes transparent. Okay. So what happens is, as the star expands, the outer layer starts cooling off. And if it cools off to a sufficient degree, it actually becomes transparent. Well, now what happens? That light that was being trapped by that opaque layer is now allowed to escape. In other words, the outer layer starts emitting light. It loses energy. So what can you tell me about the temperature of that outer layer if it's emitting light now? It starts to fall. The temperature starts to fall. And what happens to the kinetic energy of that outer layer if the temperature is going down? It decreases. And what happens if the kinetic energy of that outer layer decreases? The physical size of the star is going to decrease. Okay? And so what happens is as this outer layer becomes transparent, the light is allowed to escape, the outer layer is allowed to cool, and the star starts contracting again, starts decreasing in physical size. Okay. Now, as the star decreases in physical size, as it starts collapsing gravitationally, the temperature of that outer layer starts to go back up. And if the temperature of that outer layer starts to go back up, this transparent layer becomes opaque again, trapping even more light. And then you start going through this cyclic process again. And that's how we describe the variability. What happens is there's a layer of the star that becomes opaque. The star traps that heat and begins to expand. That layer cools off to a sufficient degree that it becomes transparent. A light is allowed to escape. The entire outer layer begins to contract. That transparent outer layer becomes opaque, traps the light, and the star begins to grow again. And so you get this back and forth, this oscillation. Okay? Star cooler, contracts, traps light, starts getting warmer, expands. Outer layer becomes transparent, star begins to contract, etc., etc. It just keeps going back and forth. Let me give you an idea. This is also a really cool example. Okay? This is RS Popus, and what we're doing is going to zoom in. Now, this variable star is unique in the fact that there is a region of fairly dense gas around the star. And so as the star pulsates, as it changes from small to big, and because it's changing in temperature and physical size, its luminosity periodically changes. So in this video, as that luminosity of the star periodically changes, you can see, if you will, waves of bright and dim light going through that cloud of gas. It almost looks like ripples in a puddle. Here is a plot of the brightness, the visual magnitude, the apparent magnitude of RS Popus. And then this bottom, it's labeled as phase. You could think of this as time. Okay. So this is what's referred to as a light curve, plotting the apparent magnitude as a function of time. Now, phase, what this is representing is how far through its oscillatory period is it. So one phase of equal to 1, that means it's completed 1 full period. Or 2 means it's completed 2 full periods. Okay, so that's kind of translating. If you prefer to think about this in terms of days, RS Popus is about 41.5 days. So from the time that it's really bright and it dims and becomes bright again, that's about 41.5 days. That's the period of the star. We're going to pull this together now. This is the cool part. And we have to go back. We have to go back to the 1880s, 1890s. And you already know which group I'm going to reference here. The group that did a lot of great observational work in the 1880s to, say, the 1920s. Pickering's group. And here, instead of mentioning Annie Cannon, we're going to go for somebody else. Henrietta Swan Leavitt. Okay. Here's a picture of Henrietta Swan Leavitt, shamelessly stolen from Wikipedia. And Henrietta Swan Leavitt studied these variable stars. And in fact, one of the papers that she produced, she studied something like 25 or 30 variable stars. And she did something that nobody else had thought of yet. Okay? She plotted the period of oscillation as versus the absolute magnitude. We'll have to walk through these numbers. I believe that the horizontal axis is the logarithm of the period. Okay? So she decided to plot the logarithm of the period. The vertical axis is the apparent magnitude of the stars. And one thing that you notice right away here, okay, yeah, there's 2 lines. What she did is she plotted, this would be the maximum apparent magnitude. This would be the minimum apparent magnitude. Nowadays, we would just plot the average apparent magnitude. So that's one thing. You notice two lines. What else do you notice about these lines, though? What can you tell me about the apparent magnitude as the period increases? It increases. That seems like a strange relationship, that as the period increases, the apparent magnitude of the star increases. Okay? Now, of course, Henrietta Swan Leavitt had at her disposal main sequence fitting. Okay? So she is able to actually measure the distance to some of these variable stars. Okay? That's the first thing. And you know that if you have the apparent magnitude of a star and you know how far away it is, you can now find the absolute magnitude of the star. So Henrietta Swan Leavitt actually discovered what is called the period luminosity relationship. I will go ahead and put that down. Okay. Again, if we plot the period of a variable star on the x-axis and the luminosity, or if you prefer the the absolute magnitude on the vertical axis, what you find is that as the period goes up, so does the luminosity. This is such a profound discovery in our ability to measure the size of the universe that Henrietta Swan Leavitt at one point was put forth as a potential Nobel Prize candidate. The only unfortunate issue is that when it was proposed that she be awarded the Nobel Prize, she had died 3 years prior. I believe it was from cancer. And unfortunately, the Nobel Prize is not awarded posthumously. In other words, you have to be alive to get it. Okay? So it's a bummer, but that's how profound of a discovery it was, is that some people wanted to give her the Nobel Prize for this. The first thing I want to focus on, however, is using the period luminosity relationship to estimate a distance to a star. Okay? You with me? Let's get at it. So here's the question. What is the luminosity of X Cyg? Okay? This is a Cepheid variable star, and I have given you the light curve. So right here is the light curve. You notice that 8-1, that's August 1st. August 1st of, I believe this is actually 2001. And then I go September, November, December, yada, yada, yada. And what we've plotted here, each of these dots represents the apparent magnitude of X Cyg over the course of months. So the first question I want you to deal with for me. Find the luminosity of X Cyg. Take a minute, go. You got it? Good, good. Hopefully you paused the video, you worked your way through it. Let's go ahead and work through this together now. Okay. Now, of course, this data is a bit messy. I tried to pick one that might be reasonable to approximate. Okay. And usually the trick is, what I would recommend doing is don't try to get it for just a single period. Okay. See if you can do it for maybe 2 or 3 or 4. That sometimes helps make the estimation a little bit better. So let me highlight for you. I'm going to go ahead and start on this low peak, and I chose that just because it lines up with October 1st. Okay. And then I went through and I said, okay, there's 1 oscillation, there's 2, and roughly it ends, oh, okay, I'll just ballpark it and say November 1st. So now I have an idea about the period. I can get an estimation of the period from the light curve. Okay. So the period is roughly 30 days, and in that 30-day sequence, I completed 2 full cycles. So 30 days divided by 2, that gives me a period of about 15 days. That's the first part. I need to estimate the period from the light curve. Good so far? Now here's the magic that Henrietta Swan Leavitt helped us out with. Because I have this period luminosity relationship, I can now estimate the luminosity of this star. I have to go and find, okay, well, 15. Okay, well, here's 10, there's 30. So halfway in between, roughly halfway would be 20. So I'm going to estimate where 15 is. I'll say right about there. Okay. And now I just read up to where it matches the line, and I have to read over to get a rough estimation of the luminosity. And we see that, okay, well, it's above 1,000. It's not quite to 10,000. I'm just going to go ahead and estimate it. I'll say, okay, it's roughly 9,000. Just ballparking. At this point, we have to ballpark, we have to estimate. Okay. And now notice the luminosity here is given in terms of the solar luminosity, the total luminosity of the sun. So this variable star, reading the period from the light curve and using the period luminosity relationship, I estimate that the luminosity of this star is roughly 9,000 times the luminosity of the sun. Good so far? Okay. So now we're halfway. The goal is, remember, how can we use these Cepheid variables to estimate distances? And now we're at a good place to do that. We have the luminosity of the star. If we can somehow take this luminosity, and I'll go ahead and express it in terms of absolute magnitude. I want to take this luminosity and get it in terms of absolute magnitude. It's a good exercise for us to practice anyway. Once I have this in terms of absolute magnitude, I have the apparent magnitude from the light curve. And that will give me an ability to estimate the distance to the star. So that's the next step. Let's go ahead, take a minute, and let's see. If the absolute magnitude of the sun is 4.5, that's from our magnitude discussion in the previous video. If you don't remember that, go back right now, double check that, remember how we got that. Okay. So the absolute magnitude of the sun is 4.5. What then is the absolute magnitude of X Cyg? Take a minute, pause the video, see if you can hack through that idea. In fact, I'll give you the first step. Let's use this. Hint, 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 hint. Good? Sweet, sweet, sweet. Let's go at this then. Okay, the first thing that I'm going to do is let's go ahead and instead of using this, the brightness, I'm going to express it in terms of luminosities because I don't have the brightness of X Cyg. I have its luminosity right now. So let's go ahead and convert. I'm going to substitute in two expressions. Number one, the luminosity of star 1 and the luminosity of star 2. So that's why I have luminosity over 4 pi. And now you'll notice I put in 10. Why did I put in 10? Because right now, let's go ahead and consider not the apparent brightness, but the absolute brightness. And the absolute brightness is the brightness as measured from 10 parsecs. So let's go ahead and let's cancel out some of this stuff. Let's get rid of the compound fractions for a minute. So here, I've gotten rid of the 4 pi and 10 squared. I have the luminosity of one star, and I've gone ahead and I've substituted in the luminosity of the sun. If I've substituted in the luminosity of the sun, I better put in the absolute magnitude of the sun right here. Now we're good to go. We just need to get M1, the absolute magnitude of my star, by itself. So we have to undo this thing, the exponent. How do we do that again? Logarithms. So let's go ahead. Let's take a log of both sides. Okay, so we've gotten rid of that 10, and now we just need to get M1 by itself. So we multiply by 5 halves to get rid of this 0.4. We'll move that to the other side. Okay. And also, let's move the M1 to the right-hand side, and I'll take this right-hand side and move it to the left-hand side. So at the end of the day, we have this expression. The magnitude of X Cyg is the magnitude of the sun minus 5 halves the log of the luminosity of X Cyg divided by the luminosity of the sun. Now let's go ahead and plug in the luminosity that we found from the past, the previous problem. 9,000 solar luminosities. Okay. And you say, wait a minute, Greg, what happened to L, the luminosity of the sun? And that's the value, that's the importance or the helpfulness of expressing luminosities in terms of the solar luminosity, is that we can cancel out that solar luminosity in the denominator. So we plugged in all of our numbers, and right here, now we're ready to go. We just throw in the magic, and we get that the absolute magnitude of X Cyg is negative 5.3. Almost 10,000, as we expected, 10,000 times brighter than the sun. Remember, a difference of 5 magnitude is 100. So we have a difference of roughly 10. That would be a factor of 10,000, which we knew already. Good so far? Walk yourself through that. We haven't done anything fancy. We're just throwing a couple of equations together, namely this one that we've developed and the luminosity equation, and we just had to go through. If you don't feel comfortable with that, pick another star, try it again. Okay? Or ask questions. That's what our Q&As are for. Okay, so now let's recap. We've used the period of the variable star and the period luminosity relationship to get the luminosity of the star. And then we said, well, let's take that luminosity, and rather than using that, let's find the absolute magnitude. Okay, so that's what we did here. Now, the last thing, how far is X Cyg from Earth? Go ahead, take a minute, see if you can hack that out. Okay, I assume you paused and you hacked it out. So the first issue that we have the absolute magnitude. We should get an idea about the apparent magnitude. Okay. And that would be the reading off of the vertical axis here. All right, apparent magnitude of 7.2 all the way to something like 6. So what does your gut tell you should use for the apparent magnitude? Use the average value. That's the easiest. Use the average value. Okay. So we know that it goes as low as 7.2. I've estimated that it'll go to 5.9, something like that. So let's just take an average. Okay. 5.9, that's the brightest it ever gets. 7.2, that's the dimmest. So I'll say on average, and this is fine, this is how we'll use it, the apparent magnitude is something like 6.55. Now that we have the apparent magnitude and we have the absolute magnitude, go ahead, if you didn't get that part, if you're stuck, go ahead now and find the distance. You got it? Sweet. We say, well, we got this. We've got the distance equation, right? We have something that relates the distance to the object in parsecs to the apparent and absolute magnitude. So we don't have to do any fancy logarithms or anything else. We just need to take these two numbers and substitute in. So we do that. I will mention, be careful. Don't forget, this is a negative. Okay? And so you have a minus and a minus. Please be careful of that. I do it myself. I forget to put the negative sign in sometimes. Okay? So if you're prone to making that error, just be aware. Double check, remind yourself about it. Okay? Good. Now we just plug away. Go ahead, hack it out. We get something like 10 to the 3.37 is the distance. So we evaluate that, and we get something like 2,300. And keep in mind, I should have subscripted this D. This is in parsecs. Okay? The reason it's in parsecs is because, remember, the absolute magnitude is the brightness of a star when viewed from 10 parsecs. Okay? That dictates that this equation is in parsecs. So we get something about 2300, which is wicked cool, right? We use the period luminosity relationship to get the luminosity of the star. We converted that luminosity into the absolute magnitude. And now that we have the absolute magnitude and the apparent magnitude, we get the distance to the star, 2300 parsecs. So let's return to the distance ladder. What does this mean? Okay. It turns out that this allows us to start reading distances up to about 1,000,000 light years. Oh, excuse me, 1,000,000,000 with a B, 10 to the ninth, 1,000,000,000 light years. That is now close, that's far enough away from the Earth that we can start measuring distances to nearby galaxies. Really important. And the reason that this allows us, we can measure further, is now we just have to collect the overall light, the amount of light from the star. We don't have to take that light and divide it into its respective colors. The other thing that I should point out, okay, notice when we did, the reason that we were able to establish main sequence fitting, the first HR diagram, is that we were able to measure some stars, the distance to some stars, using the parallax method. Okay. That meant that there are some stars that main sequence and parallax overlap. That's how you form the first HR diagram. And then I said, we will assume that this relationship of the main sequence extends to stars that we can't measure the distance to using parallax. I made that comment about how we now take the main sequence fitting as the model and use it to measure further distances. The same thing happened with Henrietta Swan Leavitt. She identified some Cepheids that were close enough so that she could get the actual luminosity of those stars. Then she assumed that the relationship, the period luminosity relationship, applied to stars that she couldn't measure the distance to. Okay, so we take that as now the new model, and that's what allows us to push even further away from us in the galaxy. But I can't highlight enough the importance that Cepheid variables have made for us to actually realize how small we truly are. Hey, thanks for your attention. I'll see you next time.